Hi everyone, my name is Chen. I'm a postdoc at the Biomedia Group, Imperial College London. In this video, I will give a brief overview about MaxStyle, which is a novel data augmentation technique that can greatly improve neural network segmentation performance on out-of-domain test images. So in this work, we are working on a single domain generalization task, which is very challenging yet realistic setting. So basically, we would like to train a domain-generalized robust segmentation model from a single domain so that it can be directly tested on various unseen sites without dramatic failures. However, achieving this goal is quite challenging, as in clinical practice, test images from different sites can have very different image appearances, image contrasts, and image quality. As you can see here, the training data from the single site can have very limited data diversity, so that it fails to cover the full spectrum of the real-world data variations. This is also known as the domain shift problem. As a result, a model trained from the single source domain can easily fail to segment a test image sampled from a very different data distribution. So to solve this problem, we propose MaxStyle, a strong data augmentation technique that can synthesize a new domain with increased image style diversity and hardness to enhance training. MaxStyle is simple, practical, and effective, which can be used as a plugin module to greatly improve model out-of-domain performance on medical segmentation tasks. Our results show that MaxStyle can bring more than 20% performance improvement. So how does MaxStyle work? Well, given a segmentation network, we first introducing an auxiliary image decoder that performs image reconstruction. The whole network can then be optimized with a multitask loss, including the segmentation loss and the reconstruction loss. A major difference we make here is that we introduce several feature augmentation layers called MaxStyle in the decoder, which can augment the style diversity and hardness of input features in an adversarial way. In this way, one can generate a set of images with the same anatomical structures, but very different and challenging image appearances for data augmentation. And the network is then optimized with the multitask loss using both input image X and augmented images head X star from the new domain, encouraging the network to learn some robust domain invariant features for robust inference. Now, let's look at how MaxStyle augments features exactly. Well, given a batch of set of features, we first compute the style statistics of each feature, which are the channel-wise means and standard deviations. And for each instance, we first perform style normalization, followed by style augmentation, where the augmented styles is a linear combination of its own style and the one from another instance, J. To further enhance style diversity, we introducing some additional channel-wise style noises sampled from Gaussian distributions. Here, in order to bound the style noises within a reasonable range, we rescale the noise with a variance of style statistics computed from the current batch. To further enhance the hardness of the augmented styles, we first apply the adversarial training technique to search for optimum combination of style augmentation parameters highlighted in pink. Specifically, those values are optimized in the direction of maximizing the segmentation loss. Here it shows MaxStyle augmented images before and after style optimization, where we can clearly see that the network is more sensitive at the style optimized image. Although there is a strong structural correlation between the input image and this augmented image. Augmenting the dataset with these challenging images can help to improve the model robustness against the different image appearance variations. Now let's look at some results. Here we perform evaluation on the intra-domain testset and 3 different out-of-domain testsets, including corrupted ACDC-C dataset, as well as the challenging cross-set and cross-sequence datasets. As you can see, the baseline model completely fails on the out-of-domain testsets. By contrast, our method can successfully recognize and segment the cardiac structures in all 4 domains. Meanwhile, it significantly outperforms a wide range of existing image space and feature space augmentation approaches. Our detailed experimental results show that our method can bring more than 20% performance improvement, greatly surpassing existing approaches. We also conducted experiments under different data settings and different tasks and found consistent improvements. For more details, please read our paper. Thank you for listening.